Welcome back 11th graders. In the previous video that you watched, we focused on learning goal 1 within section 1.5, which was learning to find the inverse of a function algebraically. And then we talked very briefly about this, but we talked about how you could determine that its inverse is also a function. That's actually an idea we'll talk more about in this video we're starting today, where we're focused on learning goal 2, where you are going to learn the graphical relationship between a function and its inverse, and you will apply the horizontal line test to determine whether a function has an inverse function or not. Let's jump right into it. Remember that you ought to be taking notes, and so I am expecting that you're copying down examples. If I ask you to pause the video and try some things out on your own, I'm expecting that you're going to do that and then wait on me to see if you've done it correctly or not. Let's make these lessons as valuable to you as they possibly can be. Now you're going to recognize this slide from the previous video that I made, where I told you how to find the inverse of a function. And if we understand this, then it's going to help us understand graphically what the relationship is between a function and its inverse. Remember that if you have a function that will map x values to certain y values, then the inverse of that function you can find simply by switching the x and y values with one another. Alright, so simply switch the x and y values in order to find the inverse of a function. Well, let's apply that to a graph. Alright, you see a function here listed in which I have 5 ordered pairs as part of the function. And what I want to do right now is I want to go ahead and plot those values. And I'm using a scale of 2 units equals 1 unit, if you know what I mean. Or every 1 square equals a half a unit, rather, is what I ought to say here. Okay, so I've got those points graphed. Well, remember that in order to find the inverse of a function, what you do is you switch the x and y values. So a function f, for instance, maps -2 to 3 and has a point -2, 3 on the graph, then its inverse should have the point 3, -2. Just switch all the x and y coordinates, and in fact, here you go. Here's at the bottom of your screen all the points that would be associated with f inverse, and you can see it's just where we switch all the x and y coordinates from this relation up here. Alright, now I want to show you how those graphs compare one another, and then there's a whole lot of depth that we can get out of this conversation. Here's the graph of the inverse. I just got those points in red. Okay, one of the things that's really cool about when you graph a function and its inverse at the same time is that they have a geometric relationship to one another. And when I say a geometric relationship, generally I'm talking about some kind of transformation can be applied to one in order to make the other. And it turns out when you're making the graph of a function and its inverse that you can use a reflection in a very specific line to make the graph of the inverse from the graph of the function. And here is that line. If you graph a function in the line y equals x, if you reflect a function, in the line y equals x, that will make the graph of an inverse from the graph of a function. Can you see the symmetry there? If I were to fold this part of the graph up top over that line right there, it would give me that graph right there. So every function, if you reflect in the line y equals x, gives you an inverse, the graph of its inverse. Okay, now secondly, it turns out that you can determine whether or not an inverse is a function by looking at the graph of the relation. Now I want you to focus on the red points here, the graph of the inverse. You ought to already be able to tell me that that inverse is not a function because it doesn't pass the vertical line test. If I were to draw a vertical line through various points on the graph of the inverse, it's going to pass through that graph more than one time. So, quite simply, we can say that f inverse is not a function. But it turns out I didn't need the graph of the inverse at all in order to make that determination. Let me clear this off the screen. Because one of the things that you can do to determine if the inverse of a function will be a function as well is you can apply what's called the horizontal line test, in which you draw a horizontal line through the original function and you see if it passes through the graph more than once. And you see I just drew a horizontal line that passed through two different points on the function. Alright, let me see if I can explain to you why that horizontal line test tells you that the inverse of that function is not a function itself. I'd like you to consider this drawing in order for me to explain why the graph of a function passing a horizontal line test or not passing a horizontal line test can determine whether the graph of its inverse would represent a function as well, whether the inverse would be a function. Forget the graph part. Alright, and so I drew a picture of a function, and I drew a couple points on the function, and I went ahead and drew a horizontal line that happened to pass through that function 2 times. And we're going to pretend that the first point over here on the left has the coordinates -4, 6, and let's just pretend that the x-coordinate for this point over here is, I don't know, 3. Doesn't really matter. But the fact that these 2 points here and here lie on the same horizontal line means that they have the same x-coordinate, which means that for function f, the point -4 and the point 3 both get mapped to the point 6. Well, what that tells you then is that if you look at the inverse, where you switch the x and y coordinates, that the point 6 will get mapped to -4, and it will get mapped to 3. And since that inverse then would have one input that gave you 2 different outputs, the inverse is not a function. So, when a function's graph does not pass a horizontal line test, its inverse is not a function. And if it does pass a horizontal line test, then the inverse is a function. Alright, let's move on. Now, I just want to illustrate that point about the relationship between the graph of a function and its inverse. You see here the graph of the function f of x equals x squared plus 2. Alright, you can see the equation written right there. And I want you to take a look at the graph of its inverse. Remember, you can make an inverse just by switching x and y. So if this is y equals x squared plus 2 right there, then the inverse would be x equals y squared plus 2. Let's not worry about getting y by itself there. Just look at the graph of the inverse here. There is x equals y squared plus 2. And remember that I told you that the graph of a function and its inverse are always reflections in the line of y equals x. Well, here's the line of y equals x, and I think you can see again the symmetry involved here, where if I were to try to reflect this graph in this line, it would look like this. See the symmetry? Okay. Let's talk a little bit more about the horizontal line test that I showed you a moment ago. Go ahead and write down the information that you see on your screen right here. Alright? When you're trying to apply the horizontal line test to a function, you're trying to determine, first of all, whether its inverse is a function or not. If a graph passes the horizontal line test, well, sorry, let me start over here. A graph will pass the horizontal line test if a horizontal line drawn through its graph intersects the graph no more than once. Now I want you to look here at the graph of f of x. If I were to draw a horizontal line through the graph of f of x, it's going to pass that graph more than once, or intersect it more than once, and so that means the graph of f of x does not pass the horizontal line test. And if the graph of f of x passes a horizontal line test, its inverse is a function. But the converse is also true, or the inverse of that, excuse me, is that if the graph of f of x does not pass a horizontal line test, then f inverse is not a function. And you can kind of see here, because I got these things side by side, when the graph of the function doesn't pass the horizontal line test, then that guarantees that the graph of its inverse will not pass the vertical line test, and so the inverse again is not a function. Alright, last thing we need to do here. I have given you the graphs of 4 functions. Pause this for a moment. Determine which of these functions you think have inverses that are also functions using the horizontal line test. Then we'll discuss it here momentarily. You should have determined that the first graph here is, or its inverse would be a function, because that graph passes the horizontal line test. There's no horizontal line that can be drawn here that would pass through that graph more than once. The second graph, if we're going from left to right, does not have a function, an inverse that's a function, because you could draw in several places a horizontal line that passes through that graph more than once. Alright, the third graph, its inverse would be a function. The fourth graph, its inverse would not be a function. Again, there's a horizontal line that passes through the graph of f of x more than once. You ought to, at this point, have a good understanding of the relationship of a graph compared to with its function, the graph of its inverse, namely that they are reflections along y equals x, and you ought to know that you can determine whether an inverse of a function is a function itself by using the horizontal line test. Good work again. I'll see you in class.